Hello class. Let's talk a little bit more about sine waves. You've drawn your graphs and you understand that those represent the heights of right triangle sides around a circle. Well, sine waves are more general than that. That's just one example of something that produces a sine wave pattern. A sine wave is basically any pattern that takes you from a maximum to a 0 point, to the opposite maximum, and back to the 0 point. Or it could start at the 0 point, like our sine wave does at the circle, and go to its maximum, back to 0, to the opposite maximum, and back to 0 again. So what causes this sinusoidal motion in this pendulum? Okay. Well, in this case, it's a special restoring force. And that means that it's a force that's always working against the motion of the pendulum. When the pendulum is out here, the force is pulling it back to the center. And in fact, the force is strongest out here. And it gets weaker as you get towards the center. Kind of like your parents, when you're acting up, their force is strongest when you're misbehaving the most. And as you start to settle down towards equilibrium, they relax. And then you continue to go the other direction and the force gets stronger. So when the restoring force that's pulling you back in at all times is proportional to your distance away from equilibrium or from center, that creates a sinusoidal pattern. And that sinusoidal pattern will have exactly the shape of the sinusoidal graph you created with your angles around the circle. There are other sine waves in the universe, in our experiences, besides the pendulum. Let's look at this graph. This is the day-to-day change in our daylight hours. And this was the graph for 2011. Do you see the sine wave here? Look at this. This is January 1st. Of course, there's fluctuation, but you can see that there is a distinct curve going from 0 to -3 approximately, up again to +3, and then back down. This was not engineered by man. This is the way our Earth and solar system works. So let's talk about this more carefully. We see from January 1st to 365 days later a pattern where we are rising, falling at the halfway point, going down to a maximum on the opposite side, and then back to the 0, the equilibrium. This is similar to what we drew with our sine wave, and I won't draw it I don't want to make it sloppy, but you know that it would be exactly the same if I were mapping this on my circle. So I've drawn a second axis here that shows the radian measures around my circle, and they have to match the distance, the time frame that this sine wave takes to do its pattern, okay, from day 1 or day 0 to day 365. If I map this somehow, I can write a function of daylight hours that will, let me make this y, which is daylight hours, equal to some capital A times the sine wave. We saw in this graph that this was about 3. It went down to -3 down here. So A is going to be the value of this peak here times this sine wave, which is always going to be between 1 and -1. It's going to give me the values of the sine function times this constant multiplier of A. So I want to drive home this last point about the constant multiplier reproducing the same shape that you had with the sine wave. Notice this is my daylight hours curve here in dark, and this is my sine wave that goes from 0 to 1 to 0 and -1. At a 12th of the cycle, like 30 degrees, so when you're a 12th of the way in, you have a 1/2 value on the sine wave. If you multiply that by the 3, which is my A in this case, I'm going to have 1/2, which is where I am, right there, 1/2. So you see that this black curve, the dark one, is the sine wave stretched by a factor of 3. That's nothing different. We've been doing translations for a few years now. So we have a stretched sine wave here, and the only thing I need to do now is figure out how to get the right values of x in here so that for any day of the year, the sine wave looks right. I need, at a quarter of the way into the year, I need to have the x value be pi/2, because that's when I peak. At halfway through the year, I need the x to be pi, because that's when I go back to center. And at the end of the year, 365 days, I need this to look like 2 pi. So how do I map the time to this x value? Now let's model this data mathematically using a sine function. We see this equation here might do the trick for us. Y equals 3 times sine of x. We see that this is just going to take our sine function and stretch it by 3. That would do the trick for us, given the graph that we're looking at. However, this x variable, this input here, is not the same input that we see on this graph. This phenomenon is being driven, is responding to the changes in time. X is an angle. All trig functions need angle inputs. So somehow I have to map the changes that are happening over time to corresponding changes in angle that would be plugged into the sine function. We're going to make the relationship of the distance through our phenomenon, the progress that we're making through our wave here, and the angles around a circle. So we're going to call this the phase. And the phase will have an expression that depends on time, but that phase will represent how far into the cycle we are, and it will convert the time into an angle. It's very important to understand this key concept. We're going to rewrite the x as an expression of time, which is our true input. And we're going to see that every time in this wave cycle can correspond to a certain angle around a circle. So if we're a quarter of the way into our wave cycle, our phenomenon here, quarter of the way would be right here. That would correspond to 90 degrees around the circle. Halfway around would be 180 degrees. One complete cycle, 365 days, would now correspond to a 360 degree angle, or 360 degree phase. We are mapping to the independent variable of time to the angle of the sine function. We'll do it this way. We'll set up a little chart for ourselves. We only need one data point to make the correlation. 365 days would be matched up with 2 pi radians, or 2 pi, 360 degrees around a circle. We'll use this as our conversion factor, and we're going to plug that into our expression for the phase. X our phase, will equal 2 pi over 365 times the time of the year, the days of the year. You can simplify it to this. Now we rewrite our expression. We see that y is going to equal 3 times the sine, and here's my phase. The time goes into this expression and gets converted to radians, which is another expression for the degrees, the angle around the circle. If I wanted to use degrees, I would use, instead of 2 pi in this conversion factor, I would use 360 degrees. The convention normally is to work in radians, and you'll see why in later courses. Hope that was helpful.